To begin our discussion on periodic trends, we're going to start about Z effective, or the effective nuclear charge. The basic trend is as you go across the periodic table, effective nuclear charge increases. But when you go down the periodic table, it also increases. Now let's take a look at fluorine. As you can see, let's say fluorine's nucleus is right here. It is composed of positive protons. But there's also, outside, there's all of these electrons which are negatively charged. So naturally, these electrons are going to be attracted to the protons. Yet, electrons are also responsible for mitigating their own attraction to the nucleus, because negative forces do not attract other negative forces. You want to take the outer shell electrons minus the inner shell electrons. Now, in the case of fluorine, this would be 9 minus 7, which would equal 2. And that is where you get S, which you plug back into the equation. Z, which is the amount of protons, minus S, the amount of electrons, to get the effective nuclear charge. The next trend we are going to talk about is atomic radius. As you go from left to right across a period, the atomic radius gets smaller. As you go from top to bottom down a group, the atomic radius is actually larger. Now, the decrease in atomic radius across periods is actually just due to effective nuclear charge.
Next, we are going to talk about ionization energy. Ionization energy is the minimum energy required to remove an electron from its ground state. The first ionization energy is the energy required to remove the first electron from a neutron. Right here is the first ionization energy of sodium. As you can see, the first ionization energy is 496 kilojoules per mole, whereas the second ionization energy is 4,562 kilojoules per mole. The more electrons that you remove from an atom, the greater the ionization. The more electrons are removed from an atom, the ionization energy increases. Also, with increasing ionization energy, the harder it is to remove an electron. As more electrons are removed from an atom, the greater the ionization energy. And the reason why the ionization energy of the second one is much greater than the ionization energy of the first one is because when we are removing a second electron, we are removing an electron from the noble gas core. As you go across the row from right to left, the ionization energy increases, and as you go down a column, the ionization energy decreases. Why ionization energy decreases as we go down the periodic table is because electrons are further from the nucleus and therefore are easier to remove. Why ionization energy increases as we go from left to right is because as we move across a period, the atomic radius decreases, which makes the atom become smaller. As a result, the outer electrons are closer to the nucleus and thus harder to remove. We're going to talk about hydrogen. Hydrogen is very special in that it doesn't really exhibit any of the characteristics that alkali metals exhibit. The ionization energy of hydrogen is 1,312 kilojoules per mole. Now that ionization energy is way greater than the ionization energy of any of the alkali earth metals. Hydrogen does not lose its valence electron as easily as the other alkali metals do. When we look at alkali metals, we notice that they tend to lose electrons. Well, that doesn't have to be the case for hydrogen. Hydrogen has the ability to form a hydride, which means it can gain electrons. We are going to talk about the noble gases, which are the last group on the periodic table. Noble gases are nonmetals and they are monatomic. Also, they're really unreactive. The reason why they're really unreactive is due to their stable electron configurations and that they have really, really, really high ionization energies.